Are some infinities greater than others? Intuitively, the answer is no, because infinity is simply a definition of something of an unbounded value. But what if I told you that some infinities are in fact greater than other infinities? In this video, we'll be going over the concept of infinity, one of its notable properties, and why some infinities are greater than its other infinite counterparts. First, let's go over what infinity is. The definition is quite simple. It is just anything greater than any real number. Or, if you want a more detailed explanation, it is a concept that describes anything that is limitless, boundless, or endless. Now, let's talk about a property of infinities. Doubling, halving, or using any sort of conventional arithmetic do not change the size of infinity. For example, infinity times 2 is still equal to infinity. This is because infinity is not a number, but rather a definition or a concept. Thus, we cannot treat it as an everyday number you use in standard arithmetics. This property leads to some counterintuitive examples of infinities. An example of that could be, are there more natural numbers or even numbers? Most people will be tempted to say that there are more natural numbers than even numbers because as you go across a number line, you see two natural numbers for every even number. But that is not the case, and contrary to popular belief, the sizes of the two sets are actually equal. Let's see why. One thing is because each even number can be linked to a natural number. More mathematically speaking, between the two sets, each term from the even set can form a bijection with a number from the naturals. Let's quickly review how the bijection proves its equality for those confused. Let's say you're inviting your family over for dinner, and you have 9 people coming, so including you, that's 10 people. You need a fork for each person, but you're not sure if you have enough. So to find out if you do, you decide to dump all your forks and give each of them to a person who doesn't have a fork. If you had the same number of forks as people, each fork would have its respective person holding it, which you can think of as a perfect bijection. Now, on the other hand, if you had more people than forks, you'd realize that a person or some people will not have a fork, meaning they were not able to form a bijection with any fork because all the others were taken. It is the same case for the set of natural numbers and even numbers. For every natural number, you can create a bijection with a number from the evens because the size of the set of naturals and evens are, in fact, the same. The size of both the set of all natural numbers and even numbers is known as countable infinity. This is because each term can be listed in some systematic order and is able to form a bijection to each of the terms of the set of natural numbers. What about the set of all reals? Is it also the same size as evens and naturals? Again, the intuitive answer is no. So, let's see if that's true. For this example, suppose you somehow listed all the reals in the closed interval 0 and 1. And the first 5 numbers on the list are as follows. German mathematician George Cantor proposed an argument now known as Cantor's diagonal argument. Simply put, the argument proves that the number of numbers in the set of all reals cannot form a perfect bijection with a set of naturals. Going back to our list, this argument guarantees that we can always form some number from the set of reals such that it is always unique. You can do this by, for the first digit of the new number, making it such that the first digit is not the same as the first digit of the first number. For the second digit, make it such that it is not the same number as the second digit of the second number on the list. And for the third, make it such that it is not the same number as the third digit of the third number on the list, and so on. This creates this diagonal pattern, hence the name diagonal argument. For us, the result of this process is this new number right here. And according to Cantor's argument, this newly constructed number is guaranteed to be unique. Meaning, if you are somehow to create a perfect bijection between every number of the reals to the naturals, you'll always be able to construct some new real number such that it is unique, proving that a one-to-one correspondence between the numbers from the set of all reals and the set of naturals is impossible, and you'll always have more real numbers left over. Another thing, unlike the set of naturals, where each of its numbers can be systematically counted, that is not the case for all reals. These factors come together to make the size of the set of all reals an uncountable infinity, and even larger than the set of all naturals. The difference in size between the set of all naturals and reals does indeed show that some infinities are in fact greater than others, and it all boils down to bijections between the two sets you are comparing.